Coaxial cable looks like a thick straw. A solid copper core called inner conductor is wrapped by an insulating jacket, then a metallic foil or braid called shield, and finally an outer plastic jacket. The key numbers are the inner conductor diameter, usually 0.5 to 2 millimeters. The dielectric constant of the insulator epsilon are approximately 2.3 to 2.7, and the shield coverage often 95 to 100%. Twisted pair cable is made of 2 or 4 thin copper wires twisted together. The twists keep the wires close, which cancels out magnetic fields from nearby wires. The main parameters are the wire gauge, a WG22 to 24 for Ethernet, the twist rate twists per meter, and the overall cable diameter approximately 5 to 7 millimeters. Fiber optic cable carries light instead of electricity. It consists of a glass or plastic core with diameter 8 to 10 micrometers for single mode, 50 to 62.5 micrometers for multimode, surrounded by a cladding with a slightly lower refractive index, then a protective coating and jacket. Core parameters include the core diameter, numerical aperture NA, and attenuation coefficient decibels per kilometer. All three media can be imagined as highways. The inner conductor, glass core, or twisted wires are the road, the insulation is the guardrail, and the outer jacket is the pavement protecting the road from weather. Attenuation tells us how much the signal gets weaker as it travels. For coax, attenuation alpha grows roughly with the square root of frequency because of the skin effect. Alpha of coax of F approximately equals K times square root of F, decibels per 100 micrometers. Fiber loss is mostly due to scattering and absorption and is approximately linear in distance. L of fiber of D equals A times D, where A is in decibels per kilometer. For example, 0.35 decibels per kilometer for 1,500 nanometers. Twisted pair faces both copper resistance, which rises with the square root of F, and dielectric loss. So a common model is alpha of Tp of F equals A times square root of F plus B times F. Bandwidth is the range of frequencies a cable can carry without too much loss. Coax can handle a few gigahertz, fiber can reach terahertz wide optical bands, and twisted pair Cat6 is rated up to 500 megahertz. Think of attenuation like the friction on a bike. The faster you pedal higher frequency, the harder you work against the friction loss. Characteristic impedance Z0 is the natural resistance a wave sees on a transmission line. For a coaxial line, Z0 equals 60 divided by the square root of epsilon sub r times natural logarithm of d over d, where d is the inner shield diameter, and d is the conductor diameter. Twisted pair behaves like two parallel wires. Z0 equals 120 pi divided by the square root of epsilon sub r times 1 over the square root of open parentheses, 2h divided by t close parentheses, plus 1, where h is the distance between wires and t is the wire radius. Fiber is not a classic transmission line, but the effective impedance of the optical mode is about 377 ohms, the same as free space. When a line ends with a load that does not match Z0, part of the signal bounces back. The reflection coefficient gamma equals open parentheses Z sub L minus Z0 close parentheses divided by open parentheses Z sub L plus Z0 close parentheses. If Z sub L equals Z0, gamma equals 0, and no reflection occurs, just like a perfectly smooth road that lets a car continue without bouncing. Noise is any unwanted energy that mixes with the signal. In copper cables, thermal Johnson-Nyquist noise is N equals KTB, where K is Boltzmann constant, T is temperature in Kelvin, and B is bandwidth. External electromagnetic interference, EMI, from power lines or radios can induce voltages. The shield in coax acts like a metal fence that blocks this. Twisted pair reduces crosstalk because each twist makes the magnetic field from one pair cancel the field from the next twist, similar to two kids running in opposite circles, each canceling the other's footsteps. Fiber is immune to AMI because light does not couple with electric fields. Crosstalk mitigation includes using shielded twisted pair, SDP, maintaining proper pair-to-pair spacing, and using lower frequency signaling for long runs. When installing cables, you must avoid sharp bends that can damage the conductors or change electrical properties. A rule of thumb: bend radius greater than or equal to 10 times the cable's outer diameter. For coax, a 0.5-inch cable should not be bent tighter than 5 inches. Fiber is more fragile. The minimum bend radius is often 15 to 20 times the cladding diameter. For example, 30 millimeters for a 2 millimeter diameter fiber. Cables should be protected from moisture, UV light, and rodents with conduit, protective jackets, or armoring. Think of the cable like a garden hose. If you kink it too tightly, water flow stops. Similarly, bending a cable too much causes signal loss or breakage. Cost varies widely. Plain old telephone-style twisted pair Cat 5e costs a few cents per foot, making it cheap for building wide lands. Shielded twisted pair and higher grade Cat 6a cost 2 to 3 times more, but give higher bandwidth. Coaxial cable is moderate 30 cents to 80 cents per foot, and is used for cable TV and broadband where existing infrastructure exists. Fiber is the most expensive, $1 to $5 per foot for multimode, $2 to $10 per foot for single mode, but offers huge capacity and future-proofing. Costs drop when buying in bulk. Scalability: you can add more users on fiber by upgrading transceivers without pulling new cable, while twisted pair may need higher grade cable for faster speeds. Typical uses twisted pair for Ethernet LANs, coax for last-mile TV broadband, fiber for backbone data center interconnects, and long-haul ISP links. Signal-to-noise ratio, abbreviated SNR, equals P signal divided by P noise. In decibels, SNR/dB equals 10 times log base 10 of SNR. Bit error rate, abbreviated BER, for binary phase shift keying, abbreviated BPSK, is BER equals Q of the square root of 2 times SNR, where Q of X denotes the tail probability of a Gaussian distribution. Throughput, denoted C, can be approximated by the Shannon-Hartley formula. C equals B times log base 2 of 1 plus SNR, bits per second, where B is the usable bandwidth. For example, a Cat 6a link, where B is approximately 500 MHz, with SNR approximately 30 decibels, which is about 1,000 in linear terms, yields C approximately 500 times 10 to the 6 multiplied by log base 2 of 1001, approximately 5 gigabits per second, close to 10 gigabits per second rated speed after accounting for coding overhead. Fiber with B approximately 10 terahertz, optical, and SNR approximately 40 decibels gives terabit capacities. Coax with B approximately 2 gigahertz and SNR approximately 20 decibels can carry several hundred megabits, suitable for cable modem services. Using transmission line theory, each medium can be modeled as a cascade of resistance R, inductance L, capacitance C, and conductance G per unit length. The propagation constant is gamma equals square root of R plus J omega L times G plus J omega C. The real part gives attenuation, the imaginary part gives phase shift. Fibers R and G are essentially zero, so gamma is approximately J omega square root of LC. It mainly adds delay, not loss. Coax and twisted pair have non-zero R and G, leading to frequency-dependent loss. Applying Shannon-Hartley to each yields the theoretical maximum capacity. C coax equals B coax times log base 2 of 1 plus SNR coax. C TP equals B TP times log base 2 of 1 plus SNR TP. C fiber equals B op times log base 2 of 1 plus SNR fiber. Because fiber's B is orders of magnitude larger and its SNR stays high over long distances, its capacity dwarfs the other two, just as a multi-lane highway carries far more cars than a two-lane road, even if both have the same speed limit. This comparison helps network engineers choose the right cable: cheap twisted pair for short office runs, coax for existing TV infrastructure, and fiber for backbone and future-proof high-speed links.